Calculus, Unit 5, Day 40 Notes, Part 2. We're now into Rolle's theorem. And here's the actual theorem. So if a function is continuous on the closed interval from a to b, it's also differentiable on the open interval a to b, which means obviously to be differentiable you have to, there were some things we looked at, but you have to be continuous at that point. So that's why it's the open interval a to b. And if we know that f of a is equal to f of b, then there is guaranteed to exist a value of c on the open interval a to b such that the derivative is equal to 0. So that value c, the derivative at that value c equals 0. Let me give you a quick little sketch at what that means. So if I have endpoint equals 6, other endpoint equals 6, no matter what I do, there has to be at least one value where that derivative is going to equal 0. It could be, has to be continuous and has to be differentiable everywhere. If obviously if it wasn't differentiable, it doesn't mean it. Here I have two examples. If someone might say, well, what if those values are both 6 and we just went straight across? Well, hey, there's a bunch of points where that value is going to be 0 if I looked at tangent lines there. So that's what we're looking at. All right, so we're going to look at the function that we just did. Does Rolle's theorem apply on the following intervals? Explain why or why not. Well, let's go back and look at that. On the interval from 2 to 14. So first thing I want to look at, from 2 to 14, that's right here all the way over to 14. So is it continuous from 2 to 14? Yes, it is. That works. Is it differentiable on the open interval, not including 2 and 14? Yes, it is. And what are the values of the endpoints? Well, at 2, the value of the function is 5, and at 14, the value of the function is 5. So let's go back and look. So we just said it's continuous on the closed interval 2 to 14, differentiable on the open interval 2 to 14, and the values of the endpoints f of 2 and f of 14 are both equal to 5. Therefore, Rolle's theorem's applicable. And what do I get? I'm going to get that c is 8. Let's go back and look. Where does the 0 occur? Where does the derivative equal 0? That's right here. And that's when x is 8, and that's what we're saying the value of c is. Okay? So now, next, we're going to look at this same exact function. And let's go back. But the interval now is from 2 to 8, including the 2 and the 8. So it's here. And now we're looking at 2 to 8. So yes, over the closed interval from 2 to 8, and again, I'm saying closed because we're including the 2 and including the 8. From 2 to 8, it is continuous, but, and it's also differentiable from the open interval from 2 to 8. But it does not guarantee, because f of 2 is 5, f of 8 is 11. So let's go back, and I wrote that down here. So again, following our definition of what Rolle's theorem is stating, or the theorem is stating, that again, it has to be continuous over the closed interval. It is. It has to be differentiable. It is. And then the third criteria is that the value of the function at the endpoints must also be equal. Then it's going to guarantee that there's a place where the derivative is equal to 0. Okay, so since it's not equal, it doesn't guarantee that over that open interval. And again, open interval here from A to B. Okay, so now let's take a look at a couple examples here. All right, so first example, given a function 9x squared minus x to the fourth over the interval -3 to 0. Well, let's check what the three things are. First, it has to be continuous. Well, it's a polynomial function, so I know it's continuous on that closed interval -3 to 0. I know it's differentiable everywhere, and I didn't write that down, but it's differentiable from -3 to 0. Let me write that down. Sorry about that. G of x is differentiable, and again, continuous over the closed interval, differentiable over the open interval. negative 3 to 0. And I know that when I substitute in negative 3 squared is positive 9. 9 times 9 is 81. Negative 3 to the fourth is 81. 81 minus 81 is 0. Put in 0. Get 0 minus 0, that's 0. So both endpoints are 0. So yes, now Rolle's theorem's applicable. Now what am I trying to find? Well, I take the derivative, and I get the derivative of g of x is 18x minus 4x cubed. But now I'm trying to find some value c where this derivative is 0. So kind of like the intermediate value theorem, where instead of using x, now we're trying to find that actual value c. So we put this in, and now I'm going to factor. I can take out a 2c. 2c times 9 minus 2c squared must equal 0. So 0 product property says 2c must equal 0, which tells me c equals 0. Now I crossed it out because coming back up here, that value of c must exist on the open interval. Well, that means on my interval from negative 3 to 0, I can't include the 0. So yes, that would work, but it's not on that interval. Now solve for c here, subtract 9 from both sides, divide both sides by negative 2, take the square root, we get plus or minus. But the positive value, square root of 9 over 2 is 3 over square root of 2. So that the positive value is not on the interval, but the negative value is. So there does exist a value, c, where the derivative equals 0 of this function. Okay, let's take a look at another example. All right, so on this interval. So first thing I'm going to do is I find out that it's continuous. No, excuse me. I find out uh, that it's not continuous because there's a value when x equals negative 2, it's going to be undefined, and that's on the interval. So since it's not continuous, it's undefined at x equals negative 2, therefore it's not continuous on the closed interval, negative 4 to negative 1, that we can't use Rolle's theorem. Okay, this is part 2. We'll look at some more examples in part 3.